My name is Matthew Johnson. I'm a research software engineer at Microsoft Azure Research, and I also teach at the University of Cambridge. And the work I'm going to present today, which culminated in kind of the BlockPy module, which I'm going to share, is obviously a group effort, both including my colleagues Mathew Parkinson and Sylvan at Microsoft, and also our amazing collaborators at Uppsala University, Fred and Tobias. So this QR code here, if you want to just kind of skip ahead to the good bit, that'll bring you to the project website. You can go and kind of look at that independently if you want while I'm talking. It'll show up a couple other times and also be there at the end, so don't feel like you have to go to it right now. So I'd like to start today kind of with a motivating example for concurrent scaling. So this, what you see here is the Boyd's agent-based simulation. It's kind of a cool kind of simulation of birds. Each Boyd is trying to kind of get near to other Boyds, but not too close, and it's trying to match the angle and speed of all the other Boyds around it. And even though it's making these decisions entirely independently and these observations entirely independently, you have this lovely kind of emergent kind of flocking behavior that shows up, and it's just kind of mesmerizing. Where was I? So basically, but it's also quite a complex computational simulation. There's a lot of computation going on, and you can slice it up a couple different ways. So a common way is by dividing it into grid cells and solving each grid cell independently. So let's say for this one we have 500 Boyds, 640 by 480 space they're operating in. And that turns out to 130 cells. So if you're trying to hit kind of 60 frames a second, that's going to be around 7,800 cell updates you're going to need to on the order of that. And they're going to be different. They're going to scale based on how many Boyds are in each cell, and that's kind of changing in a not predictable way. So it's an interesting workload. But it's a workload that scales linearly with the number of cells, and so it's kind of ideal for scaling up with concurrency. And so let's just do that. So ideally, if we kind of increase the number of cells, increase the number of Boyds, and increase the number of cores, we can still do this simulation. So let's do that. So we have 4 cores now, 2,000 Boyds. Now they're in 1280 by 960. It's kind of 520 cells, so that's around 31,000 cell updates a second. So now we really do need that extra compute in order to keep up with the simulation. But, and on the surface, it looks like this should just work. Each core can handle around 8,000 kind of cell updates. We have 4 cores, that's 32,000, 31,000 we need to do. We're in the clear. But of course, it isn't that simple. When we added the other cores, these cells became shared resources, right? Which means that potentially they need to be read and written by multiple cores at the same time. So let's say that we have core 1's updating this yellow one here, and it's reading the 8 cells around it, which it needs to make its update. But what if core 2's updating this one in the top left? Well, okay, that's going to be a problem because it needs to read the value in the middle, but then the value in the middle needs to read its value that it's updating. And what if we get really unlucky and let's say core 3 is reading the one in the bottom right? Oh, now things are getting quite complex. Oh, what if it's the kind of the nightmare scenario? All 4 cores trying to change the same area at the exact same time. This is where we start seeing some very interesting, quite complex concurrency questions coming up. Which cell gets read when? Which one gets written when? Whose rights take precedence? And these are the sorts of problems that show up in scaling of, concurrent scaling of problems. And they're the problems that we want to solve and make really easy and straightforward with behavior-oriented concurrency. But I'm kind of getting ahead of myself. This is a bit of a complex problem, and so I think what I'm going to do is I'm going to scale things back a little bit, look at some simpler programs that exhibit the same behaviors, and motivate back from those and then build our way back up to these more complex examples. What is it that makes concurrent programming hard? Why is it difficult? Well, the problems fall into kind of 2 main camps: data races and deadlocks. So a data race is a situation where the threads are racing against some sort of state of the program. Take, for example, a classic one: time of check, time of use. So in this case, a check is like an if statement. It's checking to see if something's true. And the problem is, I make that check, and then between me doing the check and doing the thing I want to do, the state of the program has changed because there's another thread doing stuff at the exact same time. So to give an example, here we have kind of on the left an example of a bank account, and here the shared data, the shared resource is the balance of that account. And the first thread is going to do that check and say, okay, can I withdraw this amount of money? And it says, yes, okay. But then at the exact same time, the second thread also does that check. And at the point they make that check, it's true. But then immediately they both go and do what they think are safe withdrawals, and the account goes overdrawn. So that's an example of a data race. And we can protect against data races by creating what are called critical sections, which are areas of code that only one thread can enter at a time. And we use locking primitives, or basic low-level primitives in threading to make this happen. And we introduce that lock, and all of a sudden, I have a lock to say around the balance. I have to acquire that lock to check it and write to it, which means that only one thread can do it at a time, data race solved. But the problem is that when you add in that lock, you add the possibility of deadlock. So let's say we have two locks, lock A, lock B. Thread 1 acquires lock A and then tries to acquire lock B. Thread 2, at the exact same time, acquires lock B and tries to acquire lock A. It will never complete. Both threads will wait for each other for all time, deadlock. But it's worse than that, because debugging threading problems and concurrency issues is itself difficult, because the very act of debugging often changes the behavior of the bug that you're trying to debug. So it could be that when we're running the debugger for this time of check, time of use bug we were just looking at with balances, that when I run the debugger, thread 1 does its check, and it reduces the balance, and then thread 2 does its check, and it correctly throws an error, and I'm like, great, my program's working, everything's fine, don't know what that weird bug was in my CI. But then, outside of debugging, randomly, without any warning, and in a way that is completely unpredictable and based on the state of the machine, we get this other trace where thread 1 checks the balance, thread 2 checks the balance, they both pass, and then they both do the balance and the count goes overdrawn. So I want to be clear, I would not discover these problems. These are classic and well-known issues with concurrent programs, and they have well-known and existing solutions. But what we're trying to do with behavior-oriented concurrency is to introduce new concepts into concurrent programming that we think produce a better programmer model that results in safer, more secure, more performant, and more easily maintainable concurrent programs, and easy scaling up of single-core problems to multi-core. And we do that by introducing these two new concepts. So the first one is concurrent ownership, or the cone. So a cone provides unique temporal ownership of a resource. So it means that only one thread of execution can have read and write access to that particular resource at any particular point in time. And cones are used to schedule behaviors. A behavior is just a code snippet, just a little bit of code that needs to run. It can run on any core on the machine. And when it runs, it will have unique access to the cones it was scheduled over. So it can be scheduled over 1 cone, 2, 3, a variable number of cones. And when it runs, it has unique access to those cones. And this means a very nice thing happens, which means that that little bit of code is running as if it were a single-threaded program. It has, for all uses and purposes, the exact same program semantics as you would have if it was running in a single-threaded way. And so these two primitives provide some really nice building blocks for concurrent programming, and they give us two really helpful guarantees. The first one is that the temporal ownership means no data races. It's never possible for two threads of execution to be looking at or writing to the same data at the same time. Just cannot happen, and guaranteed. And the second one is no deadlocks. So behaviors, because of the way that the scheduler works, will never deadlock. Now, I'm noticeably hand-waving here. The scheduler is a bit too complicated in scope for this talk. I'll be in the hallway, I'll be at the Microsoft booth. I'm happy to talk about it ad nauseum, but I think it's a level of complexity that's above what I can do in this talk. But the important thing to understand about it is the guarantees it provides, which is deadlock freedom. So what we've done is we've tried to do our best to add behavior-oriented concurrency to Python as it is today. So the BockPy module is available to download and install. It's a third-party module. It runs on 3.10 through 3.15 as they are today. And on Linux, Mac, and Windows, it's lockless, deadlock-free, ownership-based, and kind of multi-core based on top of sub-interpreters and multi-gills. So that means in 3.10 and 3.11, the code will run, but you don't get any concurrency benefit. From 3.12 onwards, you get full multi-core performance for your programs. So this is available today, and it introduces two new entities into Python via this module. The first one is the when decorator. So you take a function, you say what its shape is, what its arguments are, and you can debug that function entirely independently of Bach to make sure that it has the right semantics and works the way you want it to. And then when you decorate it with the when decorator, it will schedule it as a behavior. And then there's the cone object, and this essentially takes any Python object and gives it this temporal ownership property, making it such that from the time at which that cone is created, moving forward, it can only be accessed and used by a single interpreter at a time. And the idea is that the when decorator takes as its arguments a variable number of cones, And when those cones are available and all able to be used, then the code snippet you provide will be executed on any core on the machine. And for that duration, it will have unique temporal ownership to its arguments. So now that you have a general idea of how Bach works, let's dive into an example. For this one, I'm going to use a kind of a classic concurrency programming problem called the Dining Philosophers, which was introduced by the other famous Dutch computer scientist. And so the idea is you have a table and there's some philosophers, some number dining around. In this case, it's 5. And they're eating with forks for some reason. And they each need to have 2 forks to eat, and there's the same number of forks as there are philosophers positioned between the philosophers. So what happens is the philosopher gets 1 fork, the other fork eats, puts the forks down, and over time they should all eat and then finish their dinner. Now, but the problem that arises, though, is what happens if all the philosophers, well, you can do it with me. Everybody kind of like raise their left hand, right? And then look to the right to see if the person to the right of you is raising their hand. And if they aren't, then you can raise your right hand, right? This is the problem, right? So essentially, they all grab their left fork, and then they look to go to their grab board that's already being held. And so they starve because they're philosophers. And obviously, we don't want our philosophers to starve. So how do we solve this problem? So the classic solution, and this is just one that's coded up quickly using the existing threading support in Python, is to do this kind of solution where you have a class that defines what the philosopher is. They have a name, some hunger level, and forks that have been assigned to them. There's some forks which are going to represent as locks, those locking primitives we talked about that allow us to have critical sections. We're going to create the first 4 philosophers are going to go left, then right. But then the 5th philosopher goes right, then left, which breaks this circular weighting and breaks the symmetry and allows the program to complete. And then we have this eating thread here, where we're going to say, while the philosopher still is hungry, they're going to grab their first fork, then their second fork, they're going to reduce their hunger. When they're done, then the thread exits, and we're going to create our threads, start them up, join them. So if you've done threading in Python, this should be pretty familiar. There's nothing really exotic here. This is a standard solution to the dining philosopher problem, and it's perfectly fine. There is nothing wrong with this solution. It works. But we think that with Bach, we can produce a solution that's a little easier to understand, a little easier to code, and ultimately going to be easier to maintain moving forward. So I'm going to show you what that looks like. So first, we have to decide what are our shared resources and what is the activity that's going on. What are our cones? What are our behaviors? In the case of this problem, the cones are clearly the forks, those are the shared resources, and the behavior is going to be eating. There's going to be one of these for each philosopher based on which forks they need. So you can see here kind of one potential kind of schedule of this problem for 5 philosophers, where we have A is able to grab its 2 forks, C is able to grab their 2 forks, they eat, then they put those forks down, then E gets theirs, and B gets theirs, and then D and A, and then C and E. We can never have more than 2 philosophers eating at a time. That's the natural level of parallelism for this problem with 5 philosophers. One nice property of Bach is that you don't need to know that. You just set up what the shared resources are and what the behaviors are. The scheduler figures out what the maximum parallelism is going to be automatically from the dependencies that you create. So that's a nice, and without you having to change a line of code. So you, for example, have a command parameter that says, I want 10 philosophers, and it'll then scale appropriately and across as many cores as it can to do that as efficiently as possible. So in terms of converting this kind of the first bit of the program, the key kind of replacement here is we're going to, instead of a lock, we're going to be using a cone. They don't do the same thing, but they serve the same purpose, which is helping protect shared resources. And then we also have this kind of when decorator that's going to take the place of threads. So instead of having explicit threads of execution, we're going to have behaviors that need to be scheduled and run. Then we're going to talk about what this looks like. We have our eat thread here. It has a kind of a classic nested blocking problem surface that's very classic deadlock. This is kind of a code smell for deadlock. But on the other side, we have the kind of the Bach version. What we have here is we say, we want this philosopher to eat. They have, when their forks are available, we want you to run this code. And in this code, we're going to check to see if the philosopher is sated, if their hunger is 0. If so, we're done. Otherwise, we're going to reduce the hunger and do a tail recursive call to schedule another behavior. And that call is non-blocking. It just schedules a behavior that will run when these forks are available again, which could be whenever. But the key thing is that this behavior is able to essentially schedule the follow-up work as needed. And then finally, I think this is where you really see the benefit of Bach come through, because on the left, you have to have a lot of problem-specific knowledge. You have to know about this kind of symmetry breaking trick to make it so that you don't encounter deadlock. You have to kind of spin up the threads and start them and join them yourself. Whereas on the box side, we just say, what are our shared resources? They're the forks. What are the things that need to be done with them? The philosophers need to have them to eat. That's it. We just set up the problem, we set up the shared resources, and the things that need to happen with them. And the box scheduler takes care of making that happen in an optimal way. And all we have to do is call wait to essentially say to the main thread, when all the current in-flight behaviors are done, I want to resume execution. So now you have an example of what a Bach program kind of looks like. Let's get down to the details of how it's implemented. So a cone or concurrent owner is implemented essentially as a C object within CPython. And at rest, when it's not acquired by any interpreter, it has the object serialized within it using the cross-interpreted data format. So this is a format that was introduced to allow the easy communication of objects between sub-interpreters. And the idea is that each of the interpreters might have a cone capsule object, even many of those cone capsule objects as possible, as needed, that kind of reference that cone, but none of them really do anything until that cone's acquired. So let's say that interpreter A acquires the cone. A couple things are going to happen. First off, interpreter A gets unique temporal ownership of that cone. Nobody else can do anything with that cone at the moment because interpreter A has acquired it. The second thing that happens is that at-rest representation of the object becomes a real, live, breathing object in interpreter A. It's going to be kind of garbage collected and handled by interpreter A. It can read and write and use it like a normal object. It's absolutely, completely normal in terms of a Python object, nothing special about it whatsoever. Interpreter A is able to do what it wants to do. But, and this is the key thing, if another interpreter tries to acquire while interpreter A has that object, it gets a very clear exception saying that this cone is already acquired, you cannot own it. Which is nice for a couple of reasons. First, it gives a very clear error message to you as the programmer of what's going on, why is my program having issues. But also, it means that your program also doesn't completely crash. You can recover from this if it were to happen. But of course, this would require going outside of Bach to even make this happen in the first place, because most of this is kind of internal plumbing of the Bach framework itself. So interpreter A makes its change. In this case, it's turning the triangle into a star, and then it calls release. So the release is going to then take that new value, serialize it anew, and put it into the cone. Now the cone's at rest, we're back to our initial state, and another interpreter can acquire that value. So as I said earlier, I'm not going to get into the details of how the behaviors, the scheduler is implemented. It's a bit out of scope for this talk. But I do want to talk about a couple different kinds of common patterns for behaviors that we see in Bach programs. So the first one is maybe the simplest to understand. It's just scheduling some behavior against a single cone. So in this case, we have this populate function, which has this kind of fill behavior that it's creating. So I pass in a cone, and what it's going to do is it's going to fill that cone with a list that has a range of values. And I call populate twice for left and right. And because those are being scheduled on different cones, those can happen simultaneously. They don't have to happen simultaneously, but they probably will. And they're going to happen on different cores. And those cones are going to be populated with values. This next behavior is the really interesting one, though, because it's able to be scheduled against multiple cones. So in this case, I want this merge behavior to only execute when left and right are available. And because of the way that Bach works, that will be after the populate behaviors have run. So essentially, I know that all of this previous work that's happened on those cones will have completed by the time merge runs. And so I can then merge those lists. I merge kind of the values of B into A, and I clear B. This is fine because I have unique temporal ownership to those cones at this point in time. And then I do this thing that we've seen before with the tail recursion where I schedule a new behavior. So behaviors can schedule more behaviors. That's how you can get kind of work fanning out and growing over time. And that will, again, it's a fire and forget. That's not going to block the behavior of the cone. It's not the execution of the behavior. It's going to continue processing, but it schedules this work to be done the next time. In this case, A is available. So this works today. It's this kind of a crash course in how it works today, but it works today. It works great. We're really happy with what we've been able to achieve without making any changes to the Python language whatsoever. It's built on top of existing kind of sub-interpreter multi-GIL and the cross-interpreter data interface, which are there in Python today. And we're really happy with what we've been able to achieve. But there's obviously room for improvement. If you know anything about the cross-interpreted data API, you know that cost of serialization and deserialization is the potential bottleneck for Bach today. So if you, for a lot of cases, it's not a problem, especially if you have something that's very compute intensive. The cost of doing that serialization and deserialization is fairly low in terms of the overall work that's being done. But you can absolutely produce workflows in which you have a kind of a complex user type that has quite a big kind of graph that needs to be serialized, and you're doing very little work with it. And in those cases, the serialization kind of dominates the runtime of Bach. There's some things that can be done. For example, custom pickling routines are a huge help. Also, if it's a C extension type, registering it with the Exidata interface is, and as a kind of a known Exidata type, huge improvements can be gained that way as well. But this is definitely an area for improvement, and we have a couple ideas of how to make this good for broad cases of objects for use under Bach. So the first one is the deep immutability PEP 795, currently underway. This is us as well, we're responsible for it, and we're doing it because of the benefits that you gain for a bunch of different scenarios, but Bach is one in particular. So if you have data that's truly immutable, that's not going to change, you don't need to worry about scheduling over it. Any behavior can read it at any time because it's not going to change. Those data races are possible on immutable data. And so that's exciting to us because it means we can kind of remove a whole category of work that's currently happening in the runtime. And so what PEP 795 proposes is two things. First, true deep immutability, where you have essentially not the shallow immutability of a tuple or a frozen set, but essentially a whole object graph where the immutability of every object in that graph is guaranteed by the CPython runtime. And the other thing that it has is a separate garbage collection mechanism for immutable objects that's independent of interpreter. Currently, the garbage collection is tied to a particular interpreter or sub-interpreter, and what we want to do is decouple that so that immutable objects are being garbage collected separately, because then they can be seamlessly shared across different interpreters and read easily. So the second, more speculative kind of bit of work that we'd like to do is the introduction of regions. So we've added Bach in other languages as a paradigm for concurrency, and one of the things we've introduced in those circumstances is the concept of a region. This is an arbitrary object graph, what has a special property, which it has only one incoming edge. So essentially you can have any structure you want within the region, but there's only one way in. And if that way in is held by a cone, then you can share it between interpreters, and it's absolutely fine because all the properties of the cone's temporal ownership are now kind of handed to that whole region kind of object graph. So obviously, maintaining the invariant that it only has one incoming edge that's the tricky bit, and that's what we're currently researching. But this is a kind of a promising thing that can be done that would allow you to share mutable data between interpreters using behavioral agent concurrency, but without any serialization and deserialization, entirely by reference. It's very exciting, but this is kind of more speculative. So BachPy exists today. It's a module that you can pip install right now. Just to kind of show you kind of our support profile. As I said earlier, in 3.10 and 3.11, we have limited support. The program will run and execute, but it will not be any faster. It might be a little bit slower. In 3.12, you get full multi-core performance, and then that's true for every kind of Python after that. And recent kind of Python releases have added some nice goodness around the Exidata kind of protocol, making certain built-in types faster, in some cases almost free, and that also kind of redounds to us in terms of performance. And finally, I just want to kind of return to our example from earlier. So if you want to try out the Boids example on your local machine, you can just pip install Boids, which will add in Piglet so you can actually see the graphics, and then run BachPy Boids and see how it works for your machine. If you want to go online and see how we solved the Boids problem with BachPy, that's in our GitHub repo. It's, we think, a very elegant solution to this problem, and shows how you can use Bach to do kind of quite performant programming for graphics and other domains. And on the right, we see our benchmark. This we also ship with the library. Feel free to run it on your local machine and see how it does with its performance. We ran this on a 14-core machine. We run it on a lot of machines. This particular example is a 14-core machine, and it's kind of it's interesting because essentially we get this lovely linear speed up. So obviously, ideal speed up would be right on that dotted line. We're very close to it. Right after this, it starts to peter off. So essentially, after 8, it kind of elbows and peters off to 14, and that's because at that point in time, we kind of did some measurements. Essentially, it's fighting the OS for resources. I mean, obviously the operating system needs cores to do things that it needs to do, and it starts having issues scheduling its work against those. But we have this really nice property that, up until that stage, we get quite nice kind of linear scaling. And I think this is an important point, this whole thing is entirely opt-in. If you don't use our library, it has no effect on your program. If you do choose to use it and write your concurrent workloads in this way, then you can potentially have a huge benefit from Bach. And so I would like you to go and try it. Go give it if you have some kind of compute-heavy workloads, see how difficult it is to translate it to Bach and see if you can get some benefits from doing concurrent programming. And thank you. Yeah, question. And I will happily take questions.
Yeah. It's funny. You were supposed to introduce me earlier.
I'm sorry. I'm so sorry.
Andy, sure. But there's still chance for a couple of questions, I guess, if you want.
Absolutely.
So if you have any questions, you can come to in the center. There's a mic.
Check, check. Hi. So you mentioned multi-GIL earlier. Mm-hmm. How does the impending release of stable free threading play with this?
Great question. So I guess two answers. So the first answer is we don't enable the GIL. So our module as it is free threading compatible. It runs under free threading fine. It's part of our CI matrix. At the moment, though, all of the work it does with subinterpreters and type marshalling is sort of theater. Under free threading, it's not needed. So we have an issue on the repo, which you can go read if you want to see. It's our current standing plan for what we're going to do when the API stabilizes, which is essentially having kind of a forked implementation, which doesn't do the current subinterpreter stuff that we do for free threading builds, so we can get kind of the most performance out of that. But we actually honestly think that Bach is a win either way. It's perfectly compatible with free threading and provides, we think, a better programming model than bare threads. So, yeah, but absolutely great question.
Awesome, thanks.
How would you compare Bach with something like classical fork join algorithms? It seems like you're basically going and taking the work of figuring out the scheduling out of, building that fork join and giving it to Bach, which seems like very nice.
Yeah, and obviously Bach grew out of kind of actor-based approaches, which are kind of a similar kind of philosophy. And the whole idea here is we wanted to solve this problem of scheduling over two things or more at the same time, right? So not just being, I want to send this message here and then respond to it, but I want to have this thing that only runs when all of these things are ready. And essentially what happens, essentially you say fork join, because essentially what happens is Bach, the scheduler, creates a DAG of all of the computation that needs to happen. But the key thing being that the programmer doesn't need to worry about that and all the various ways it can go wrong. They just need to focus on this key question of what are the shared resources, what do I need to do with them?
Thanks.
I know you didn't want to talk about the scheduler in too much detail, but it does feel like some of the magic lives in the ability of it to build a stag and to know how to avoid deadlocks. And
absolutely. I mean, I'll put it this way: if they invite me back next year, I'll give the scheduler talk. But
yeah, I was wondering
worried again, I'm happy to talk about it. But the key thing, maybe the key intuition to think about, is that each cone has this kind of list of behaviors that have asked for it, right? And they're kind of handing off a baton to the next behavior, and when the next behavior has all the batons, it runs. And so, and we kind of have done all this work to make that very fast through multi-producer, multi-consumer work stealing queues, and to make it so that there's no kind of a central scheduler that's doing anything that would cause kind of a synchronization cost. So everything's happening in a distributed way, but still having these guarantees. But I'm happy to talk about it offline. I'll be out in the hall and at the Microsoft booth if you want to learn more.
Cool. And then I was also wondering, is Threads the only natural sort of backend for this, or subinterpreters, or could all of this work at sort of different levels of concurrency?
It can work at any level of concurrency. Great question.
Yeah, there's some similarities I see with async to an extent, but I was wondering how well does this play with regular use of threads? If you're, I'm guessing that you can't mix the two, or you're going to end up with trouble.
So that's a great question. interesting things will happen. So basically, the key thing here is that when this code executes, when a behavior executes, it executes as a through-line function in a subinterpreter, right? So if it then calls out into a third-party library that does something with threads, it'll be as if that was called within the subinterpreter. So provided that that thread code is well behaved and joins and returns, then everything should be fine. But certainly there are some interesting potential cross effects that could happen. But anything that's safe to run in subinterpreters today is safe to run with Bach. Okay, great.
Right. No, go ahead.
Thank you. It was great. Thank you.